Okay, so greetings everybody. I hope you were interested in what we did last time. So I'll start again, and I'll start by reminding a little bit what happened with the Newton result. So recall that we always have an algebraically closed field, okay? So this is algebraically closed, and we have the Newton result. So this is where we left off, and we amounted to saying that this was a correspondence between affine subsets by Fk and ideals of K of x1 up to Kxn. Right. So here we take an affine subset to associate an ideal for this subset, and for an ideal J we associate its set of zeros or zero locus. It depends on how you say it. Okay. So let's do a little bit of some comments about this correspondence for just under this correspondence we have points correspond to maximal ideals. Okay, so we have points correspond to maximal ideals so these are points N of K, and these are ideal maximal ideals of K of x1, xn. So more precisely, if I have a point with coordinates a1 up to an, under this correspondence, we obtain here the maximal ideal. Well, there's no canonical notation, but I'll write it as M of A, which is okay. So it's just the maximal ideal for which all of these are. And part of the Newton result says that these are all the maximal ideals of this ring, if K is algebraically closed. If K is not algebraically closed, there's some subtleties that we need to take into account. But okay. Okay. So this is, in some sense, this is a generalization. So let's do some couple of remarks. The Newton result is a generalization of the fundamental theorem of algebra. Now, why does that mean that? Well, it means that if I have J, which is a proper ideal, okay, then there is a zero for this ideal. So this is not something that is obvious from all these definitions, but yes, and it's not necessarily true if the field is not algebraically closed either.
By zero, you mean?
It means that V of J is not empty. And that's like that. Okay. Okay. Now, a second remark is that this helps to define polynomial functions on the n space. Okay, so we can identify polynomials and polynomial functions. Okay, if I have two polynomials such that f of p is equal to g of p for all p in the n space, then what does this mean? This simply means that f minus g is in the ideal of I and of k, and this ideal is simply the zero ideal. F is equal to j. Of course, polynomial functions are simply polynomial functions that's on the n space given by polynomial expressions. Okay. So this, so now that we have this kind of like identification, this brings us to one of the very important object for the study of the geometry of space is the coordinate ring of algebraic space. Not fine, sorry. Okay, so like always, our main focus will be on an affine subset. Okay, a polynomial function on X is a map with values in K, so this is always going to be the field K. Is a map given by X goes to f of X for some polynomial f in the so we take a polynomial function on the n space and we just restrict it to the affine subset. Okay. And we have a notation for all these types of functions. We write a of x, the ring of such functions, the ring called the coordinate ring. So, okay, this is the coordinate ring of X. Now, we can actually find a we can actually find a little bit of structure on this coordinate ring A of X. Okay, A is fine. Okay. Okay, so this will have to keep drawing faster. Okay, so we can okay. So so in some sense, we obtain the coordinate ring starting from the polynomial ring itself. Okay? So two polynomials f and j well, we can consider them as polynomial functions on x, and we want to know when two polynomials like these identify, meaning that they give the same polynomial function, identify on x, if and only if, well, simply put, they have always the same image, meaning that their difference is always 0 on x. So, if and only if f minus j is on I of x. But this is actually the defining property of a quotient. Okay, so actually the affine ring is simply put the quotient of the polynomial ring over its IP. Okay. Okay. So, well, as I'm erasing part of the correspondence for Houston flats, before we end this small discussion on the first fundamental theorem of algebraic geometry, I want to discuss just quickly a relative version of this correspondence. Okay, in the relative version of the Newton Satz in some sense. Okay, so let's, for our purposes, let's fix this time y a affine subset. And this time I'm interested in affine subsets that are inside of y, not just an of k. But this is what I mean by the relative version. We are not considering subsets of an of k, but of a affine subset fixed beforehand. Okay, but the ideas and the proofs are quite quickly just the same. Okay, so if now I take S a subset of the coordinate ring of y, then I can define the zero locus of S as the set of points in y that are cut out by the polynomial functions inside of S. Okay, so it's mostly the same idea, so this is the zero locus of S in y. Similarly, we can define an ideal. Okay, so if I have so this is yeah, I haven't said it, but this is inside of y, of course. Now, if I have any subset inside of y, define its ideal so this is in a very similar way. This time we define the polynomial functions on y that particularly are 0 on x. No. And this is an ideal of A of Y. Okay. Okay. Okay, so we have the zero locus in the ideal. So just like in the global case, we can actually recover for such, well, let's say a subset. We can actually recover its coordinate ring in from its relative versions. So x is still inside of y, and its coordinate ring, so not the relative one, is actually simply put we quotient out the coordinate ring of the ambient y by the ideal of x. So this is just the quotient, we further quotient, simply put, we simply put, we further quotient the polynomial ring by something bigger to obtain something smaller. Okay. So now we have also a relative Nullstellensatz for this. This is just a big word for something relatively simple. Relative okay. So if I take Vyf or Iyf some under arbitrary affine subset, so here I consider that it is a fine. Okay, not just any. This was a general process. This is less of a general process. If I take Vy Iy, then we just tumble down again back and forth. And for any ideal inside of AY, and if I take Iy of Py of J, then I obtain simply put the radical. And this radical is inside of AY, of course. So this is the difficult part of the Nullstellensatz at the end, but it can all be tracked back to the original Nullstellensatz. And this gives a correspondence so we have affine subsets of y on one side, and we have radical ideals of A of y on the other side. And as you can imagine, it's the same type of procedure. The ideal, and the other side, take y of j. And exactly like we did for points on the global version, we have points here. Correspond to maximal ideals this section up. I just like to give an exercise, but you know, it's relatively quick. So I want to, under this correspondence here, you can actually show that x is finite if and only if a of x is a finite k-vector space. Okay. So this is a neat little exercise, and it more or less kind of helps to bring together all these remarks. Okay, so now that we have some grasp of how the ideals and the subsets correspond to each other, we'll start to add some structure on all these objects. And the first structure we will need, if you want to have some sort of
affine subsets inside affine subset then are affine inside the affine space.
Yes. This is actually the affine subsets in Y are the affine subsets of the AN of K that happen to be inside of Y, actually. And to see this, you take the equations inside of Y and you add the equations of Y itself to see that it is a whole set of the whole space. Actually, this will be a remark when we come to the topology. Because now we are going to need, well, actually already mentioned okay. So let's come back to. So we have a second section which will be concerned with the Zariski topology. And some of its properties. Okay, so let's just define it first and foremost. So I take an affine does it do better like that? Okay. So we take an affine subset and we define the closed subsets for its Zariski topology. We simply put the Vs, the Vx of S, which live inside of X. Okay. So these are the affine subsets of X are going to be forming a topology for X, and this is what we call the Zariski topology of this affine subset. Now, we actually already established that this is a topology. So, verifying the axioms of the closed sets of a topological space. This is a topology, right? Okay. Now, for several reasons, we know that, for instance, Vx of 1 is the empty set, Vx of 0 is the whole of X, and we know that if I take two subsets, then this will give me the intersection. We don't really see it here. were actually some of the first properties we had established about the subsets. Now, I'm doing this for the relative version, but it's more or less immediately applies for the general case. Okay, so it takes a little bit of time to dry out, so you can't really see it. Okay. So, Vx of S1 and S2, so the product of these two subsets is going to be equal to Vx of S1 intersect, union. Yeah, this is the closed subset. Vx of S2. And we also have the arbitrary intersection. So if I take a family of subsets, then its zero locus will be the intersection. So these things define the axioms for the closed sets, not the open sets. Of course, this means that the complements will define the open subsets. Okay. Now, as we said a little bit earlier, there was a possible confusion. Now, if I consider the topology on X, right, defined by its relative zero locus, then it is also the induced topology from N of K. Okay. The induced Zariski topology of N of K on X. All right. This is because, and the main reason for this is that the affine subsets of X are the affine subsets of An of K that lie inside of X. Okay. So this is what I was saying a little bit earlier. Okay. Now let's continue. Let's see if I can try this out. Okay. So just a final remark that actually kind of completes the Newton Satz. If I take any x inside, well, just take this one. What happens if I take the v of I of x? Right? We know that if x was an affine variety, this would give us x again. But if x is any subset, we just obtain the closure. Okay. Good. Okay. Now, this is one good, but as you may imagine, this topology is very different from the type of topologies we generally encounter in real analysis, for instance. And I'd like to show just a couple of methodologies that occur when we deal with the Zariski topology. At least try to contrast it with the usual Euclidean topology. Okay, let's erase the whole thing. Okay, so let's talk about some ontological behavior. I'll just evoke two. One is concerning the continuity. Okay, so let's consider that. Okay, yeah. So let's suppose that we have A1 of C. Okay, so C has a Euclidean topology, so let's just take, and this is simply put C the line. So let's just consider the closed ball, the closed unit ball inside of A1 of C. Okay? Now, if I consider this, this is not closed of the Zariski topology. Right? This may be a little bit confusing, but in fact, the closed sets of A1 of C for the Zariski topology are, well, on one hand we have, no, that is excellent. A1 C itself and the finite sets. And I include in these finite sets the empty set, of course. So these, so how do you establish this? Well, simply put, if you consider an ideal inside of the coordinate ring of A1 of C, A1 of C, its coordinate ring is just the polynomial in one variable. So its principal is generated by a single ideal and by a single polynomial, sorry. And if this polynomial is not the unit, then the set of 0 is just the roots of this polynomial, and it is a finite set. Okay. So as you can see, the closed sets are pretty small considering how complex the structure of C is. But we'll see a little bit further. Okay. Sorry. No, sorry. And yeah, well, what I wanted to add to this was that in this case, there's any injective map is continuous. So naturally we wonder, well, okay, this gives too much leniency on the nature of continuous maps, because injective maps can have a very, very wild behavior, and we wish to have maps, to restrict ourselves to maps that preserve some structure. But we'll see further on what kind of structure we'll need so that this doesn't behave too badly. Okay, but at least this provides some motivation for the next part, when we'll talk about regular functions. Okay, then for one of the compatibilities we have that we don't have anymore are products. Okay? So products of Zariski topologies are not Zariski topologies in general. Okay? So this is more or less an exercise. For instance, let's consider the affine line again, and consider let's see. Yeah, okay. And so consider the diagonal of their product. Okay, so it's in A to K. It's all the set of points of coordinates A, A. Okay, for A, any element in the field. So this is naturally we imagine that this should be a closed subset of the plane, but it is not. Okay. So this diagonal is closed in A2 of K for its Zariski topology still, but not closed for the product topology of the two lines. It's a nice exercise to actually establish what are the closed sets for the product topology. And you'll find only unions of vertical lines, horizontal lines, and points, which is pretty restrictive considering the richness of the structure of A2 of K. Okay. So, as you can imagine, we need some specific concepts to at least try to understand or at least give some pertinent characteristics of these topologies. So this is why we are going to establish the concept of irreducibility. Okay. So now, specific concept for these types of categorical topologies notion that we don't really need for Euclidean topology is reducibility. So a space, a topological space will be reducible if I can define it as the union of two subsets, okay, for x1 and x2. These are proper closed subsets of X. Okay.
It's the definition of reducible.
Yes, of reducible. Yeah, it's the what? Yeah, maybe you can see. Yeah, and it is called, otherwise then you'll call it irreducible. So, and this is actually the more pertinent concept. Since, as you can imagine, if you take any Euclidean space, then obviously it will be reducible. You just need to take a hyperplane and consider the upper and lower spaces that are defined by these hyperplanes. For instance, there are many ways to decompose in a reducible space. Okay. So an example coming from our affine subsets, let's consider the x 1, x2, right? Inside of the plane itself. Okay? So what does this look like? Well, if I have the coordinate rings, then let's see, maybe this will work. I hope this shows. Okay, yeah, these are the union of the two axes. So, as you can imagine, as I already said out loud, it is the union of the two axes. But the two axes are themselves closed subsets, closed proper subsets. So this is not irreducible. And in fact, these are two proper closed subsets. The coordinate axes. And actually, this is kind of the prototype to what we'll consider just next, will be the irreducible decomposition. That our affine subsets may not be irreducible, but we can actually decompose them. Okay, so let's make some room. Hopefully it will be visible. Okay. Yeah, just as a second example, just by examining what the closed subsets of A1 of K are, this is an irreducible subset, for instance. We know what its closed subsets are, and by our convention, K is infinite. So this is not a finite set. So it cannot be the union of two closed proper subsets. Okay, so this is a topological property, but this actually can be read in a very simple way on the level of its algebra. Okay, so I take x to be affine, and if x is non-empty, then we can actually have x irreducible is equivalent to having I of x prime. So this is the basic algebraic interpretations, but also we can read it on the level of its coordinate ring, so on the level of functions that lie that are defined on x. Meaning that the coordinate ring is double, because it is the quotient of the polynomials by this integral, so it's clear. Okay. So these are, well, you can find a quick proof of this, or you can try to do it yourself by using this, mostly this interpretation here, but with the polynomial functions. But you can also go check the Kaplan selection notes. Okay. So this gives us the very first definition of what a variety is. So is a variety, is an affine variety, sorry, if it is irreducible. So finally, varieties are irreducible affine subsets. This is the main object of interest for us. We will deal with affine subsets in some cases, but usually when I mean variety, I mean that it is something irreducible. So this will be an important property for us. Okay, so some application of that. We give some examples for this. And if K is irreducible, okay, because, well, its coordinate ring are the polynomials, it's a domain. So, what about some finite sets? Yeah, let's see. Finite sets are irreducible if it is reduced to 1 point. Finite sets are irreducible if and only if they are reduced to 1 point, to a single term. So, as I said, we know that most affine subsets are not varieties, but then why do we study varieties? Well, we can more or less reduce our interest to irreducible subsets by what we will call irreducible decomposition. It's kind of what we already established here. Okay, so let's talk about irreducible decomposition. So, at least in the affine case. Okay. So, any can be, so if I take an affine set, I can write it right? So I can write it as a finite union, of course, of xi is a non-empty irreducible host of x, and so this is a general process, but if I can assume a simple set theoretical operations, and if furthermore we don't have any inclusions among these xi's, the xi are unique, and they are called the irreducible components. Irreducible So we can actually reduce our study to these components, and thus our main interest in varieties, like this. Okay. Now, just as we did characterize the irreducible subsets on the algebraic level, let's try to figure out what this decomposition means on the level of algebra, which actually provides in some way a proof of this. Well, if we know enough commutative algebra, of course. Okay. So, well, let's just say that this is a round. Okay. So we take this affine subset, we consider its ideal inside of x1, xn, and remember that it is a reduced ideal, right? No, it is, sorry, it's not a reduced, it's a radical ideal, and its coordinate ring is a reduced ring. Yeah, that's the correct terminology, radical. Okay, and this is where the algebra comes from. Any radical ideal admits a let's see, a simple primary decomposition. This is where everything comes into play. That admits a primary decomposition so I of x can be written as a finite intersection of primary ideals, right? So primary ideals. So this is a generalization of prime ideals, and in some way, well, the objective of primary decomposition was to generalize unique factorization. So we know that unique factorization is not always true for all rings. Many examples arise from either algebra or from number theory. So the next best thing was primary decomposition. It took some time to establish, most notably by Lasker, which was an infamously very difficult proof. But Noether, Emmy Noether came and gave a very easy and conceptual proof where she established the famous property that I also made for Noetherian rings. But okay, let's shorten our discussion a bit. Okay, so if I take these primary ideals, we can consider them to be unique, right? And we know that their own radical will be equal to a prime ideal. Okay, so let's see what happens if we come back to x. Well, as you know, the Newton's gives it this. This ideal is the intersection of its primary components. And we know that this intersection of ideals will give us a union at the level of zero locus. So we have V of Q1 union V of QR. But I know that I can take the radical of each of these ideals for the zero locus. It will give us the same affine subset. And this is actually already our primary decomposition. Because this, the zero locus of a prime ideal will be irreducible. So we have a union of irreducible subsets that is equal to X. So this is the irreducible decomposition. So again, the topology or geometry, depending how you think, is corresponds to something very algebraic. Okay. Okay. So let's see which one is this. I think I'll need some water to go fetch some water for this. Right. Thank you. Oh yeah, this one. Thank you. Okay. So before we move on to the next concept, I wanted to just mention some very interesting properties of irreducible subsets that may become useful in other contexts. Right. So irreducible topological sets have very peculiar topological properties. What I mean by that is that open sets are generally big, very big in irreducible subsets. Okay, so I take X, an irreducible topological space. So this is an arbitrary topological space, which is irreducible, right? And I consider two open subsets of X, okay? Let's see, do I need something else? No, it's okay, just this. I considered two open subsets, and I have two very interesting things to say. If U is non-empty, the two open subsets are non-empty, then their intersection is non-empty either. Okay, which is not a trivial proposition to do. Well, it's not a trivial statement in any arbitrary topological space. And this can just be boiled back down to the definition of irreducible. You just need to take the complements of the opens and you just have the true set. But this actually implies the second point, which means that if U is non-empty, then it is dense. This is why I was saying that open subsets are generally big. Right? Non-empty open sets are dense inside irreducible subsets. Okay. And just as a fun application, let's say, this actually allows to justify the concept of extension of identities, or the so Well, this will come in handy, especially when we are going to try to define what the important continuous functions will be on our varieties. But even before that, there's a pretty nice application for this. Well, something I call extension of algebraic identities. Okay, so I still suppose this works okay infinite. So not necessarily algebraically closed, but this works for any infinite subset, any infinite field, basically. So if I set an affine subset, this should be A of K. So an affine subset that is proper, so it's not the whole N of K, and P, the polynomial in n variables, that is 0 outside of X, then P is 0 on N of K whole. Right. But this actually generalizes a lot of density arguments we usually use on topology. So imagine we want to show identities on matrices. For instance, on the characteristic polynomials. For instance, you want to show that the characteristic polynomial of AB is equal to the characteristic polynomial of BA. Well, you show it first for invertible matrices. So this will define an open subset on the vector space matrices. You can see the vector space of matrices as an affine n squared space. There we have n squared variables. And the determinant will be a polynomial that cuts out an x which is not equal to an of k whole. So if you can show it for invertible matrices, you know that it will be true for all matrices. So this is kind of a generalization of this topological argument that you use in linear algebra, for instance. Okay. Let's see. Okay. Well, I need to make a little bit of space. Okay, so this irreducibility seems to be a rather interesting place to work with. And one of the main interests we have, or at least the next concept that it motivates us, is the idea of dimension. Dimension is infamously difficult to define for arbitrary topological subsets. Okay.
Yeah, that is this. Right.
Oh, okay. I see. There. Well, there's a whole history that could be written about the concept of dimension. If we restrict to manifolds, then this dimension is it is relatively easy to define. But what if we consider algebraic varieties? Well, this is where irreducibility comes in very handy. As the thing I just mentioned here, so let's talk. Let's see how much time. Okay, yeah, I have it. So let's talk about dimension, which is really one of the very first geometric concepts that will come in. So intuitively, we want to use the same kind of intuition that served to define manifolds, right? So intuitively we want it to be, the dimension should be the number of coordinates, okay? Well, the minimal number of coordinates, of course, needed to describe a neighborhood of a point locally and on this space. Neighborhood of a point. As you can imagine, if the spaces are connected, this dimension may vary, of course. But roughly, this is the very intuitive notion we have of what a dimension should be, since it is very inspired by linear algebra, or even just our experience of the world we have in 3 dimensions, thinking that we have depth, width, height. But it turns out that this is very difficult to define, at least for now, for algebraic varieties, the main object we are interested in. So the minimal requirement we will have would be the following. Instead of going all deep down into the geometry, complex geometry, not the complex in the complex sense, but the sophisticated machinery inside of a variety, we will only give a definition based on topology. Okay? So, X irreducible and Y inside of X proper closed subset. Irreducible should have lower dimension. Now, why am I using this hypothesis of irreducibility? Well, as you remember, what I actually erased here was that the open subsets of an irreducible set, topological space, were really big. Conversely, that means that the proper closed subsets are small. So this is kind of what that translates to at the level of dimension. And this is how we define the topological, dimension, which we'll actually see bears as the name of one mathematician called the cool dimension. But we need to do a little bit of work. Okay. Okay. So, I take X, a non-empty topological space, okay, and I can define, well, first of all, I can define its dimension is simply written dim of X. And then I consider the following things. I consider integers that actually measure the length of certain chains of subsets. Okay? So, there exists a chain. Yeah, unfortunately, I'll have to spill over the next black hole. Okay, so we have the subsets. And it's, of course, we need to consider proper chain, strictly increasing chains of subsets, because we can always consider the stationary set. It won't be really interesting. This I is irreducible closed subset of X. Okay. So we consider these increasing chains of properly irreducible closed subsets, and we take the one with biggest length. If there is no bound on the length, then it will be considered to be infinite. So it's either an integer or infinity. And in a dual way, we can define the codimension of a subspace. Let's see. Okay. I consider this time an irreducible closed subset, Y. Then we can define its codimension, the codimension of Y in X. Well, it's very similar to the above definition, but this time the chains must start with Y and not the empty subset. So, Y let's see, because Y is inside of Y naught, which is inside strictly Y1, and 2 Yn, which itself is inside of X, like that. Okay. Okay. So this is a definition. Of course, this is also, if we consider our intuition of what the dimension should be, this more or less corresponds to what linear algebra would give us as an idea of a dimension. Every finite dimensional vector space can be filtered with linear subspaces in this way, and the maximal chain corresponds to the dimension. So this is more or less a...
Sorry. Just a second.
Okay.
Here y is equal to y0 or y is parent.
No, it could not. It could be something strictly bigger. You can suppose.
Also it can be...
Yes, it can also be equal to y. And actually, you will kind of want it to be equal to y if you want the maximum of the chain. The maximum chain y0 will be equal to y, because if it is not, then you can extend it by adding y artificially. See?
Everything is good. If you could just start the sentence I interrupted.
Okay, no problem.
Yeah, thank you.
No problem. Okay.
And maximal sequences, do they have always one and the same length?
No. This this is kind of where things well, for affine subsets it is true. It is a theorem, however, because it is not an obvious property. There are topological spaces that also come from algebraic geometry. For instance, if you consider some strange schemes, then you can actually find topological spaces that are not catenary. This is the property that you want to focus on for this next to be always part of it. Okay. Now let's keep, well, as I mentioned, for affine subsets, things will work out very nicely. Let's give some examples, quick examples. Okay, so for the first one, as we already have established, the topology of A1 of K is relatively simple, so we can easily prove that this is just one. Okay. And if I take any point inside of A1 of K, its codimension will equally be 1. Okay? Because for y equal to a single point, I just take y naught to be this single point, and yn to be the whole space, and there's no in between. Okay. Now, instead of an example, I'll rather give a counterexample of a topological space that has infinite dimension. Just to see that our intuition is not necessarily obvious. Okay, so consider N as a topological space with closed subspaces So these subsets verify the axioms of a topology. Well, if we add n to the topology, of course. But as you can imagine, there is no inclusion between these YNs except the obvious chain of Y1 included into Y2, etc. And it turns out that this actually gives us that these YNs are irreducible. The Yi n are irreducible, giving an infinite chain. Right? So Y0 put it in Y1. So with this topology, n is equipped with an infinite dimension. Okay, so this is just to see that, you know, the infinite dimension spaces exist. They are very easy to define. And in fact, it turns out that this topological space can be, we built it out of n, so we might consider that there's no real geometry coming from this. But it turns out that this is actually the underlying spectral space of a valuation ring, actually. So it is actually more related to geometry, but in a remote way. We would need to introduce more concepts for that. But okay, let's see. Okay, so let's establish some properties again. Coming back to algebra, this is topology, so we want to come back to algebra again. That will, in some way, dispel some of the anxieties concerning these properties. Okay, so we consider so again, you already fixed x and affine fine. Then the dimension of x as a topological space, we can actually find it by considering the crude dimension of its coordinate ring. So this is a algebraic definition. So this is, well, no, not max, but the supremum of length of decreasing chains. Sorry, of increasing chains of primes in A of x. Okay. So it is almost the same definition for the dimension, except we consider the primes inside of A of x, which is pretty obvious because these irreducible correspond to the primes of the product. So this is how we bring it back down to the algebra, and we also write it dimension of A. Sometimes people would add cool, an index, but let's not do that. Okay. Let's see. Okay. Now, what about the codimension? Well, it is mostly the same thing. And I have a recipe for the dimension. We can also more or less establish the same thing for the codimension. So, if I consider non-empty irreducible closed, okay, but if it is closed, it's a fine right, then its codimension, it's simply put the codimension of its ideal in A of x. Y, and this amounts to saying that this is the dimension of A of x, quotient out, well, this is I of x. If the quotient, which, seems to be the same thing. Okay. Let's see. So I'll finish here. Okay, I'll continue here. Okay. So from now on, let's suppose that we have x and y varieties now. X and y, arbitrary, affine varieties. Okay? As you can imagine, if I take the product of two varieties, the dimension should be additive, and it is indeed the case. So these are theorems. Now, these need actual proofs to establish them. If y will be included in x, or if y is a subvariety of x, then the dimension of x will be equal to the dimension of y plus, let's see, the codimension in this sense. So coming back to what we said about if all the maximum chains of irreducible closed subsets are of equal length, it is not always the case, but we can actually use this here theorem, to establish that for affine varieties, it is actually the case. So any maximum chain will all have the same length. And this is not an easy theorem. Okay? So have the same length. Okay. here property is called being a catenary ring, at least for that means that the coordinate rings of affine varieties are catenary. Actually, they are even stronger than that, but that is even beyond them.
In what sense even stronger?
They are, yes, they are, you can actually show that they are universally catenary. In that, well, if you consider base changes, then these properties are still keeps the same. Okay, and lastly, something that will become very important for hypersurfaces. If I consider one equation, so let's say I'll give f inside the coordinate ring of fx. Again, x here is a variety, so this is a domain. So f is a regular element, a non-zero divisor. Okay? F non-zero, so it is a non-zero divisor. Then every component, irreducible component of v of f, okay, has codimension 1. So this is a nice result, which is very difficult to establish for a bigger number of equations. But if I have one equation, then I know that if I cut the variety with one equation, that I'll lower the dimension by only 1, not something too much. I won't obtain points from a surface by one equation. Okay. Let's see. Okay, I'll just give the last definition, then we'll end. But this actually motivates the very last definition for today, which is the concept of pure dimension. Okay, so let's see. What was I missing? Okay, yes. What I was missing was giving you some references. So there is, I'm sorry, I'm going to continue using the ICMS-Sofia. I haven't looked in the outline Clayman. So this is more or less page 122, corollary 1117. That helps to understand outline notes. Lemma 227 and 220. Well, yeah, these are technical results which need a little bit of work to establish. Okay. Now, considering this type of statement here, so that every component is irreducible, has the same dimension. Well, this will become a sort of definition. So, is of pure dimension. Okay? If every one of its irreducible components has the same dimension. Okay, so we will call so x of pure dimension 1 is a curve, of pure dimension 2 is a surface, and likewise if it is a pure codimension one variety are hypersurfaces. In some sense, cutting out a variety by one polynomial always gives hypersurfaces. And in some sense, there is a converse to this, but I think it is enough for today, and we'll continue on with this next week. Okay, thank you. Questions?
Okay, if there are no questions, we continue next Tuesday, right?
Yes. Okay.